Okay, so last time we were in section 2.5. Let me get this screen back on too. Should have turned itself off. Should have been a blank one, so I'll have to wait a second now. Is that flashing? Oh, I see it now. Okay, so last time we were looking at vertical asymptotes. What caused vertical asymptotes is what? Where the limit went to what? Infinity, as we were going into a specific value, as x went into like 3, we went to infinity, or what? Minus infinity. It's possible to have both sides going to what? Infinity. It's possible to have what? One side going to infinity, the other side going to what? Minus infinity. As long as one side's going to infinity or minus, you have what? A vertical asymptote. And then we were looking at horizontal asymptotes as well. And what caused a horizontal asymptote is what? When we went out to the far left, or what? The far right, as x went to what? Minus infinity, or what? Positive infinity. Okay. And let me put the 2.6 notes away and get back into our 2.5 notes. Okay. So we saw if we have polynomials. Do polynomials have a horizontal asymptote to begin with? Think of your, what should be your two favorite polynomial graphs? Do you know off the top of your head? X squared and what? X cubed. Do they have horizontal asymptotes? No. But they have what? They either go to infinity or what? Minus infinity. So let me give you a polynomial here. And the first thing I want you to do is find me the following limits. Okay, so let me give you a polynomial. We'll call this polynomial P. I'm going to give you two polynomials. I'm going to call the first one P of x. Let's make that minus 7x to the 17th plus 4x cubed minus 15x squared plus x plus 2. And let me go ahead and give you Q of x. We'll have it be 4x to the 16th minus 2x squared x to the 12th plus 4x to the 8th plus minus 8x to the 4th plus x squared plus 4. All right. So we got a couple of good polynomials here. I want you to find me the following limits. The limit as x goes to infinity of P of x. The limit as x goes to minus infinity of P of x. The limit as x goes to infinity of Q of x. And the limit as x goes to minus infinity of Q of x. Give you a second to think about those four limits as I rewrap my brain around what we were working on. I think I started thinking about the next section, so I didn't think about today's. Oh, we got some good orangey stuff today. Sweet. Excited, Alex? Excited? Yeah. 2, 4, 6, 8, 9. Missing a few today. How about those Wyoming Cowboys winning in double overtime Saturday night? Anybody watch the game? Anybody go to the game? Yeah. I can't believe they put the wedding at the same time as the Wyoming-Texas Tech game. But so at the end, we were huddled around this cell phone screen. About 20 of us. I still can't tell if it was a pass or a run for the 2-point conversion because I couldn't see it on the screen well enough. But we cheered at the end, and we were in Colorado, so that was nice. So I did have one student in my first class who was at the game. Okay, so what do we think about? First off, what do? We basically ignore what? All of this. All those terms, because all those terms they're the twists and the turns. What dominates everything at the end is what? The leading term. So we look at the leading term. So on P, what are we really interested in? On P of x is really going to be close to what polynomial? Minus 7 x to the 17th. When x gets really big or x gets what? Really small. All right, is that an odd power or an even power? Odd. So it either has to look like what? X cubed or what? Minus x cubed. Here's y equals x cubed and y equals minus x cubed. It has the same left and right hand behavior, the odd ones. All right, and we have minus, right? So since we have minuses, we're going to minus infinity. Where are these function values going to? Positive infinity. And as we're going to positive infinity, where are these values going to? Negative. So let's go back up here. So as x is going to, get my stick down here. As x is going to infinity, it has a similar left and right hand behavior as this. So as x is going to infinity, where are those y values going to? Negative infinity. So this will be what? Negative infinity. And then how about as x is going to negative infinity, where are those y values going to? Positive infinity. So that will be positive infinity, or you can just write infinity. All right, questions on that first one? Then how about the second one? Well, that one is what? 4x to the 16th. So q of x would have very similar left and right hand behavior of what? That polynomial there. Even degree, right? So it's either going to have similar to what? X squared or what? Minus x squared. Well, how do we decide which one? We look at the leading coefficient. Is it positive or negative there, Dustin? Positive. So it's got to be the same as what? X squared. So they're both going to go to what? Positive infinity. All right. So it is easy to find what? The left and the right hand behavior of what? Polynomial functions. What dominates it? The leading term. All the other terms, that decides how many twists and turns the polynomial is going to have. But the leading term crushes all the other terms when the x either gets super small or super big. Okay. So now let's look at some rational functions here. Now remember, what's a rational function again? A rational function is what? A polynomial, what? Divided by a polynomial. All right. And usually after you study polynomials, the next thing you do is you move up to the rational functions. It's kind of the hierarchy of mathematics. So let's take this function here. Let's take f of x to be 3x plus 2 over x squared minus 1. And let's ask two questions. What happens as x goes to plus or minus infinity? And what happens as x goes to plus or minus 1? And where did the plus or minus 1 come from? The fact that would what? Cause division by 0. Okay. So the first thing you're going to start asking yourself is what's the degree of the numerator and what is the degree of the denominator? The degrees are what? The degrees of the polynomials. So everybody find me the degree of the numerator. And the degree is simply what? The highest power of the x's. So who said 1? Tristan, so what's the degree of the numerator? 1. And you got that because of the x, right? And then Marissa, what's the degree of the denominator? 2. Okay, which one's bigger? The bottom, right? 2 is bigger than 1. All right, so we're going to start paying attention to that a little bit. So for now, let's look at the limit as x goes to infinity of 3x plus 2 over x squared minus 1. Okay, so we don't have a lot of tools available, but one tool is we're allowed to multiply by things. And I'm going to simply multiply by 1 over x squared, 1 over x squared. In the numerator, let's go ahead and take care of the numerator. That's going to become the limit as x goes to infinity. When we distribute, we have to what? Distribute on both terms. And when you distribute on the first term, what's going to happen? One of the x's is going to cancel. So we're going to get 3 over x. And then we're going to get what? 2 over x squared. When we distribute on the denominator, what's x squared times 1 over x squared, class? 1, right? And then 1 over x squared times that is what? 1 over x squared. All right. And let me just double check. I believe we did this last time, but maybe we did not get to this property last time. Sorry if you're getting whiplash. Oh, yes, we did have this property last time. All right. So let's go back and recall this property. I just wanted to make sure. It was a long week without you. We had this property, 1 over x to the n, or x to the negative n. As x went to infinity, what happened to this ratio? It went to what? 0. And likewise, it went to 0 if we went to what? Negative infinity. You take 1 and divide it by bigger and bigger numbers, that ratio becomes what? Smaller and smaller. All right. So let's look here. Back to this problem. Now we could write out all the little steps, but we don't want to sit there and write all the little steps out in mathematics because it starts to get a little ugly. But we know limits have what? Some nice properties. So as x is going to infinity, where's 3 over x going to? Now 3 is a constant. You think of that as what? 1 over x as far as that. Well, where's 1 over x going to? If you have one pizza and you get millions of kids, nobody's getting anything, right? That's going to what? 0? Is that also going to 0? It is. Where's this going to? 0 as well. So this is going to 0, this is going to 0, and this is going to 0. By what? The powers of those reciprocals. So in the numerator, Tristan 1, what's 0 plus 0? 0. All right, in the denominator, Brian, what's 1 minus 0? 1. So what do we have there? 0 over 1. What is 0 over 1, class? 0. 1 over 0 is a problem, but 0 over 1 is what? 0. So this really does become 0 over 1, which is what? 0. Now, we could also do that with the minus infinity as well, because of that same ratio. So we could do it for plus and minus. So what does that say? We have a horizontal asymptote, y equals 0, as x goes to infinity and as x goes to minus infinity. Okay. So now, the next one I said is what? We're interested in x goes to 1. So let me rewrite that function down here just so we have it available. F of x equals 3x plus 2 over x squared minus 1. That was the original function. I didn't change it up. So now let's look at the limit as x goes to 1 of 3x plus 2 over x squared minus 1. Give you a chance to get that, copy that. Okay, what type of functions inside that limit again? Rational functions. First thing we always do is just a little mental math. Go ahead and put 1 into that rational function and see what you come up with in the numerator and see what you come up with for the denominator. So in the numerator, what's the numerator become, Magnus? 5. And how about the denominator there, Miguel? 0. So we have 5 over 0. Is 5 over 0 one of the forms we do more algebra? When do we do more algebra? 0 over 0. 0 over 0 is when we do more algebra. Can we divide by 0? No. If this was 0 over 5, we'd say the answer is what? 0. But it's 5 over 0. So as we take 5 and divide it by numbers getting closer and closer to 0, what's happening? This is going off to either infinity or what? Minus infinity. So what does this say? Does not exist. And likewise, the limit as x approaches -1 of that function will also be what? Does not exist, because you won't get 0 in the numerator either. All right, so what does that say? That says we have vertical asymptotes at x equals 1 and x equals -1. All right, so we know a lot about this function. If we thought about graphing it real quick, we know we have a horizontal asymptote, y equals 0. We know we have a vertical asymptote, x equals -1, and what? X equals 1. We can never jump across a vertical asymptote. We can jump across, we can never cross, excuse me, let me say this correctly. We can never cross a vertical asymptote. We have to jump across vertical asymptotes. We can cross horizontal asymptotes, but never vertical, because that's where division by 0. So in the old days, we just find about 3 points. So we need an x value between -1 and 0, or -1 and 1. So somebody find me f of 0 real quick. Oh, so you 4, you get f of 0. Marissa and Cadence, you get f of -1. And the rest of you find me f of 1. Find me those, not 1. Who said -2 and 2? Sorry. So f of 0, Alex. -2? We have consensus, right? -2. F of -2, Cadence? Didn't get it? Nope. -4/3? You just plug it into that function? Right up there? All right. And then let's see, 2, Magnus. 8/3. Okay. So I know f of 0 is -2. I'll put it out there. So I suspect this function does something like this here. I could do a little bit more inspection. It could do something like that, but I could be wrong. And -4/3 over here. So I suspect this does something like this. And 8/3 up here. I suspect it does this. Although now I wish, if I had to guess, I'd plot like 2 more points here. Because I'm not sure. This could do something like this, or it could do something like this, or it could do something like that. So right now I'd like to plot about 2 more points, but we're not going to. But let's just see how I did via my intuition here. And how could we check our answer? We could go to GeoGebra. So let me get some GeoGebra opened up here. Wrong mouse. And eventually we're going to be graphing functions without using technology because we want to be able to, but we'll confirm our graphs with technology. And graphs tell the story between what? Relationships between what? Variables, two quantities. So the graph helps us see that. So, all right. Don't try to use the wrong. Internet down already this week? I don't think I've ever seen GeoGebra go down. See if it runs faster on the main computer. Oh, they almost tied each other. Okay, so let's go back to this one. So what was our function again? F of x equals, and it was what? 3x plus 4 in the denominator?
You're not typing anymore.
Oh, I'm not typing anymore? Thanks, Brian. Well, I was typing. I was just on a different screen. I got an F. So F of x equals, and the numerator was 3x plus 2, if I remember right? 3x plus 2, and the denominator was x squared minus 1, right? All right, and let's hit enter here. So I got 2 out of that. And remember, I said this middle one, I'd have to what? Do 2 more points because I couldn't quite tell it. Now with calculus, I could have told you if that was going to do what I first thought it was going to do or this. All right. So that's eventually where we're going to go, is where we can graph these, understand all their features without having to use technology, because technology makes you have to hunt for things. All right. So back to our problem here now. Okay. So our next example, let's take this polynomial here. I got to see what's going on real quick with that. Apparently nothing. All right, so let's take, excuse me, not this polynomial. Let's take this rational function. Let's take this rational function. Can't wait for my new tablet to get here. Not even ordered yet, though. So it's going to be g of x. We want to go ahead and write down g of x equals beginning to think I need to check, make sure I got the same 2 shoes on. Last time I was this discombobulated, I had 2 different shoes on. Same shoes. All right. So we'll call this g of x. And g of x now equals 30x cubed minus 2x squared plus 7 over 2x cubed plus x minus 7. This is a rational function. What is the degree of the numerator and what is the degree of the denominator? Magnus? They're both 3. So the degrees are actually equal. All right. We're going to make these observations. All right. So we're not going to worry about the denominator this time because there will be no zeros. But let's look at the limit as x goes to infinity of this function. Okay, well, we don't have a lot of stuff, but we do have that power, those understanding of that limit of x to the negative n, 1 over x to the n. So let's get some 1 over x to the n's involved. Let's go ahead and multiply by 1 over x cubed, 1 over x cubed, a form of 1. And why did I use x cubed? Because that's the highest power here, and you'll see what happens here in the next step. In the next step, when we distribute that 1 over x cubed through, what's the first term going to happen? Well, the x cubes would cancel. We just get what? 30. The next, we'd get what? Minus 2 over x, because one of the x squareds would cancel, but one of the x's would stay behind. And then we get what? 7x cubed. Go ahead and distribute across the denominator for me. And we distribute across the denominator. What happens? 1 over x cubed times 2 over x cubed. What would happen there? The x cubes would cancel. We would get what? A 2. When we distribute across here, what would happen? An x would cancel with an x there, but it would leave behind what? An x squared down in the denominator. And we end up with what? A 7x cubed in the last term. Everybody see what I did there? Questions? Okay, so now x gets to go to infinity. Well, what is this? This is a constant, right? Limit of a constant is a constant, so that stays home. As x gets big, where does 2 over x go to? That goes to what? 0. That's that reciprocal. So this would go to 0. This would go to 0. Down here, same. That would go to 0. That would go to 0. So in the numerator, we get what? 30, right? 30 minus 0 plus 0, or whatever that is. In the denominator, we get what? 2, right? Notice what I wanted there. I wanted to shake out some constants that weren't 0, because we love when we're not having zeros in things. And 30 divided by 2 is what? 15. So what do we have? We have a horizontal asymptote. Y equals what? 15. Which on your old TI-84s probably wouldn't show up, because your screen's from minus 10 to 10 without doing more exploration. All right. And then if we went to minus infinity, it would be exactly the same thing, because all those would go to 0. Okay. One more here on this one. Let's take this one. We'll call this one h of x. And h of x is x cubed minus 2x plus 1 over 2x plus 4. Go ahead and get this copied down. All right. Which has the bigger power, the numerator or the denominator? Numerator. So if you have bigger powers, that means the numerator is going to get bigger than the denominator. And what do you think then? It's not going to probably have what? A limit. So let's play the same game. We'll look at the limit as x goes to infinity of x cubed minus 2x plus 1 over 2x plus 4. Okay, so we'd like to have something constant in the denominator. So we don't want to do 1 over x cubed, 1 over x cubed, because that's going to make this denominator what? 0 when the limit. We don't want to divide by 0. So I want to get rid of this x here. What am I going to do? I'm going to multiply by 1 over x, 1 over x. Because I do not want to get division by 0 in the denominator. So in the numerator, what happens? Well, distribute through there. Go ahead and distribute through the numerator for me, and distribute through the denominator for me. I am up on my balloon blowing up and tying balloons and building balloon arches and hearts and all that stuff. I just forgot how tiring a wedding is if you get stuck helping out setting it up. All right, so we distribute through the 1 over x. What am I going to get in the numerator? I'm going to get x squared minus 2 plus what? 1 over x. And down the denominator, what am I going to get there? I'm going to get 2 plus what? 4 over x. Okay, so as x gets big, what happens? This goes to 0, this goes to 0, but where does x squared go to? Infinity, and the denominator goes to 2, right? That's important. If the denominator went someplace other than a constant, we couldn't do this. What is infinity divided by 2, class? Infinity. This is going to 2, that's going to infinity, so what do we conclude here? Does not exist. Or we, actually, we'll skip that one. Okay, next part. Let's look at this one. F of x equals 2x squared plus 6x minus 2 over x plus 1. Look at the degree of the numerator and the denominator. First off, you should recognize it's what? A rational function. Then you look at the degrees in the numerator and denominator. And you notice what? The numerator is bigger, right? So it's going to dominate. How much do they differ by? The degrees. 1, right? So the degrees differ by 1. But the numerator is still what? Bigger than what? The denominator. Okay. So let's look at doing some long division. All right. Now, some of you haven't probably done long polynomial division in a long time. It doesn't get covered very often anymore, partly because only those students going on to calculus really need to do it much, and we'll do it here and there. So let's take the the numerator, 2x squared plus 6x minus 2, and let's divide it by the denominator, x plus 1. And some of you might have learned some other cool ways of doing this, and I know them, most of them I know, but I'm only going to show one. So I always think of this way. You got to take that 2x squared, that leading term there, and divide it by x. How many times does 2x squared go into x? It goes in there, what? 2x times. So we're going to multiply by 2x. 2x times x is 2x squared. And then 2x times 1 is what? 2x. So I figured out what you had to multiply the leading term by to get to that. And then I distributed it across there. All right, everybody with me on that? And now division is like subtraction, so we're going to subtract it out. So to subtract it out, we're going to change the signs and what? Add down. What is 2x squared minus 2x squared? That is what? 0, right? That cancels out. And then 6x minus 2x is what? 4x. And then we bring down that minus 2. All right. So now you can think of what is 4x divided by x? Or what do you got to multiply x by to make it look like 4x? You can multiply it by 4, right? Or you can think of 4x divided by that leading term is what? 4. So we're going to multiply by 4. So 4 times 4x, or 4 times x is what? 4x. And 4 times 1 is what? 4. All right, so we're dividing it out. Dividing is like repeated subtraction. So that's a hideous 4 there. So we'll change the signs. What is 4x minus 4x? 0. Minus 2 minus 4 is what? Minus 6. Okay. So do we have, is this less powers than that x? It is, right? Once we get to less powers, we're done. All right, so now what happens here? Well, and let me put this in a little simpler one. Let's say I wanted to take, let's say 9 divided by 4. So let's say 9 divided by 4. 4 goes to 9 how many times? 2 times, 8, subtract it out, and the remainder is 1. So what does that say? That says 9/4 could be thought of as, how many whole times did it go in there? 2 plus the remainder over that, plus 1 over 4. And you can check, what is 2? 8/4. 8/4 plus 1/4 is what? 9/4. So you do the whole part plus what? The remainder over the divisor. So on this one, let me rewrite this here. 2x squared plus 6x minus 2 over x plus 1. Well, what was our whole part? How many times did it go in there? 2x plus 4, right? Everybody see the 2x plus 4? Plus the remainder. Well, what was the remainder? The remainder was what? Minus 6 over the divisor. What did we divide by? That x plus 1. Okay, so now let's look at the limit as x goes to infinity of f of x. Well, this could become the limit as x goes to infinity of 2x plus 4 plus this negative 6 over x plus 1. I'm going to give everybody a chance to get caught up on this piece. I even learned how to make confetti stick inside a clear balloon. Do you know how you do that? You got to rub it on your head first to get the static, and then shake it up. That was one of my tasks. I had more hair until I did that all day Saturday. All right. So now I want you to think about this last term here. As x gets big, where does this piece go to? 0, right? Negative 6 over that, that's going to 0. So what's happening is, as x gets big, this function is looking a lot like the line y equals 2x plus 4. What we have here is we have, and we'll study this a little bit more in depth when we get into this graphing more, is we have what's called a slant asymptote. And asymptote is not spelled right there. All right, and why did that pop up? Because the degrees differ by what? 1, and it was 1 in the numerator. Okay, I'm going to give you a chance to get that written down, and then I'll show you what that looks like graphically. Oh, and I forgot to ask you, what would cause division by 0? Negative 1, right? And if you put negative 1 in, you'll see that it doesn't make the numerator 0. So we'll also see we have a vertical asymptote, x equals negative 1. So I know a lot about this graph already. I know it has a vertical asymptote, x equals negative 1. And I know it has a slant asymptote, y equals 2x plus 4. And I could plot more points to figure things out, but we'll have more techniques going on. But let's bust out some technology now and just kind of show you where this is leading to. All right, so let me get out some GeoGebra here again. Let me go ahead and turn this off. Actually, let me just go ahead and edit it. So our leading function, our numerator of that function again was what? 2x squared. 2x squared minus what? Plus 6x. Minus 2? Was it plus 2 or minus 2? Minus 2. And then over what? X plus 1. Thank you. And then let me go ahead and put in our vertical asymptote. Our vertical asymptote was x equals what? Negative 1. And our slant asymptote was y equals 2x plus 4, and let me zoom out here. And you can see, and let me get my stick out here, but you can see, first off, you can see because that degree is bigger than the numerator, it's going off to either infinity or what, minus infinity. But you can see also that it really starts to look like what? That line y equals 2x plus 4, and here's our actual what? Curve there. They're starting to look what? Very close together. Actually look so close together pretty quick that if you wanted to make your calculations easier, you might use 2x plus 4 versus what? That function. So that's one of the reasons why I like slant asymptotes and stuff. All right, when do we get that slant asymptote? When the degree of the numerator is what? 1 bigger. All right. So we can have some other asymptotes. All right. So let's tie this up with a theorem. But you've been sitting for 45 minutes. Why don't you stand up and stretch for a second, talk to a neighbor, find out how they're doing before we write up this big, ugly last theorem.
So would the limit be infinity or does not exist? Does it?
Well, we'd probably just put does not exist. We'd have to do more exploration.
Okay.
All right, we didn't lose anybody, did we? Okay, so let's tie all this together. Theorem. The end behavior and asymptotes, hang on, theorem. End behavior and asymptotes of rational functions. We want, this theorem is basically going to mean, hey, we can look at a rational function and basically tell everything about it. We've made the observations, we've showed you the little tricks of 1 over x to the power, but reality is we don't like to do that a lot because it's time consuming. We like to just, hey, say that's a rational function, you look at the degrees and you know what its horizontal asymptotes are, and you know if it has vertical asymptotes. So here's how this theorem goes. Let f of x equal p of x over q of x be a rational function where, no period there, p of x, so remember these are polynomials, so we got to have some polynomial notation here. We'll call p of x a sub n x to the m plus a sub m minus 1 x to the m minus 1 plus dot dot plus a1x plus a naught. So we got a polynomial, it has lots of terms, we don't know how many terms, so we got to use some variables, and what do we know? We know its degree is m, and its leading coefficient is what? A to the m. And we know all the rest of this stuff. It helps the turns. This denominates what the left and right hand behavior, and that would be the constant term of that polynomial. And q of x, it's also a polynomial, and we need to have different variables because they may not have the same degrees. So we'll call this one b sub n, x to the n, plus b sub n minus 1, x to the n minus 1, plus dot dot dot, plus b sub 1, x, plus b naught. Where, and one more thing, with, since they can't use another where, with a sub m not being 0 and b sub n not being 0. All right, that just means the m and the n are what? The leading terms. Okay. Okay. First possibility. If m is less than n, that means the numerator is less than the denominator in degrees. So that means the denominator what? Dominates. We're dividing by bigger and bigger numbers. So what happens? Then the limit as n goes to, as x goes to positive infinity or negative infinity of this function, what does it equal? 0? It equals 0, and we have a horizontal asymptote y equals 0. So all that says, hey, if the denominator has a bigger degree, that limit is 0, and we have a horizontal asymptote of 0. The denominator dominates if it has a bigger degree. Second possibility. If m equals n, same degrees. So we have the same degree in the numerator and of the denominator. Well, that means neither one of them dominate. So what happens there is the limit as x approaches either positive infinity or minus infinity, and we didn't do an example of this one, can't do every example, of f of x. What is it? It's the ratio of the leading coefficients. And we have a horizontal asymptote y equals a sub n over b sub n. Ratio of what? The leading coefficients. So we got where the numerator is smaller. We got where they're equal. Then we got to go with the case if m is greater than n. That means the numerator is bigger than what? The denominator, degrees. Then the limit as x goes to either positive or minus infinity of f of x, it either equals plus infinity or minus infinity, and we'd have to do some more exploration. And we have no horizontal asymptote. Okay, we're almost done with this thing. Okay, fourth possibility. If m equals n plus 1, the numerator is what? One more degree. Then the limit as x goes to plus or minus infinity of f of x equals either plus infinity or minus infinity, depending on the case, and f has a slant asymptote. So if you have one more degree, you're going to have a slant asymptote. It's going to be a line, and what we're going to practice our long division of polynomials, which many of us haven't done in ages. So if you felt like, man, I haven't done that in a while, you're right. Okay, so that is all about deciding if we have what? Horizontal asymptotes or slant asymptotes. That's the left and right hand behavior. All right, so we also title this vertical asymptotes. Okay. If f is reduced, that means what? No common factors in the numerator, no common factors what? In the denominator. Then f has horizontal asymptotes whenever q of x equals 0. And if it's reduced, the reduced part means you can't have 0 over 0. Because 0 over 0 would say, hey, you could reduce it. 0 over 0 says there's algebra. But if you don't have 0 over 0, then what do you have? And you have 0 in the denominator, then you have a vertical asymptote. Excuse me, except I wrote horizontal asymptote there when I should have wrote vertical asymptote. Okay. So let's take a couple of functions here. Let's take f of x equals, let's go with 3x to the fourth plus 7x squared plus 1 over 1 minus x to the fourth. And let's decide what are its horizontal asymptotes and its vertical asymptotes. All right. So the degree of the numerator, look at the degree of the numerator and denominator. Decide what the degrees are. And the numerator is what, Tristan, 2? And the denominator? Okay, Tristan, you ready? Tristan, 1 now. Does 4 equal 4?
Yes.
Yeah, it does. So they don't outrace each other. So our horizontal asymptote, you look at it and say, I can tell you what the horizontal asymptote, it's going to be the ratio of the leading coefficients. It's really going to be 3x to the fourth divided by minus x to the fourth. So that would be what? 3 divided by negative 1. So its horizontal asymptote is simply y equals negative 3. It's the 3x to the fourth divided by minus x to the fourth. That would be the dominating. What would happen? X to the fourth would cancel. Minus 3. All right. Visual inspection now. What would make this 0? If x was what? 1 or what? Minus 1. All right. That would be division by 0. Now put 1 up in the numerator, put minus 1 up in the denominator. Just do it mentally in your head and decide, does it make it equal to 0 or not? If I put 1 in, I get 3 plus 7 plus 1. That's not 0, right? If I put minus 1 in, I get 3 plus 7 plus 1. Is that 0? No. So the numerator is never 0. Is the denominator 0? It is. If that happens, numerator is not 0. Constant over 0. What do we know there? We have vertical asymptotes at x equals 1, x equals negative 1. There's not a lot of work. We want to be able to just kind of say, hey, I have a rational function. I know everything about rational functions for left and right hand behavior and what? Vertical asymptotes. All right, next example. We'll call this g of x. G of x is going to be, let's make it 2x over x squared minus 4. I want you to look at it. I want you to see if you can identify your horizontal asymptotes and your vertical asymptotes without doing much work. This is where we want to get to. Yeah, we were missing a lot today. Mark's gone. Let's see. Who sits? Their names will come in. All right, so we look at the degrees. What's the degree of the numerator? 1, right? What's the degree of the denominator? 2, right? X squared crushes x. It wins the race a lot faster. You think about the y equals x graph, y equals x squared, it grows faster. So this is getting much bigger than this. So what's our horizontal asymptote? Y equals 0. Because the x squared crushes the x. Vertical asymptotes, we look at where does x squared minus 4 equal 0? Well, that would be what? Plus and minus what? 2, just from previous. If you put either one of those into the numerator, does it make it 0? No, you get 4 or what? Minus 4. But if you put it down here, you get 0, right? So you get 4 over 0. 4 over 0 is not do more algebra for a rational function. It's saying, hey, what do we have? We have vertical asymptotes at plus and minus 2. So I would know a lot about this graph already. I would know I have a horizontal asymptote, y equals 0. So I know as I go way out to the left, it either does this or what does that. That I can't tell without a little more work. Likewise there. And I know I have a horizontal asymptote at x equals negative 2 and what? X equals 2. And then I would need more information to do much more. Okay. So let's look at the in behavior of the following function. F of x equals 10x cubed minus 3x squared plus 8 over 25 times x to the 6th, square root of that, by the way, plus x to the 4th plus x squared. Give you a chance to get that copied down. Let's see. I think that we're probably going to have exam 1 next Wednesday. I'll confirm it tomorrow, but Lee, are you guys in town next Wednesday, Marissa? Excellent. Leaning towards next Wednesday for exam 1. Chapter 2. All right. Is this a rational function? Yay or nay? What messes it up? A big old square root down in the denominator. This is not a rational function. So we can't use everything we know about rational functions. It has a square root involved. So let's just recall the definition of the square root of x squared is actually what? The absolute value of x, because we want it to be positive, which would be equal to x if x is greater than or equal to 0, and minus x if x is less than 0. If x is negative, minus x is what? Positive. That's the formal definition. All right, so let's look at the in behavior. But before we do that, I want to play with this function a little bit more here. We like to have reciprocal powers involved because we know 1 over x to the n goes to what? 0. We like that concept, that 1 over x to the n going to 0. So I really want to kind of get something out of here that's what? Going to be a constant in the end as x gets big. So I'm going to try to keep this 25 as a constant. So what I'm going to do, I'm going to factor out an x to 6 out of all of those terms. So I'm going to get, in the numerator, I'm going to get 10x cubed. I get minus 3x squared plus 8. And the denominator, I'm going to have to factor out an x to the 6 out of those terms. Now, when you take out x to the 6 out of 25x to the 6, what do you get left behind is what? A 25. When you take it out of the next one, and I don't want a square bracket, it looks ugly. I want a parenthesis there. When you take it out of the next one, well, you had an x to the 4th, and I took out, what, an x to the 6. So I took out too many, right? So that's going to pull some out there. So that is going to be there 1 over, just checking my work here. Yep, 1 over x squared. And check. If you do x to the 6 times 1 over x squared, what happens? 2 of those cancel. Leave behind what? In x to the 4th. All right, figure out what the last term looks like for me. I'll get you started. There's a plus sign for you. And a parenthesis, fill in that gap for me. Okay, so when we factor out an x to the 6 out of what, 2, well, it's basically like dividing it out, so that's what, 2 over x to the 6. And remember, you can check by multiplying. X to the 6 times 25, 25x to the 6. X to the 6 times 1 over x squared, well, 2 of them are going to cancel, leave behind what, x to the 4th. X to the 6 times that, the x to the 6 will cancel, leave behind what, a 2. Now, what is the square root? Well, remember, we need this to come out as positive. So when we take the square root, well, 6 divided by 2 is what, 3, but to keep it positive, we are going to need some absolute values around it. So that comes out as the absolute value of x cubed. All right? And that's because we want the principal root. When I ask you for the square root of 4, you tell me 2, not negative 2. And then we're still going to get the square root of 25 plus 1 over x squared plus 2 over x to the 6. So all I did there was I played a little trick that will develop along the way. And I want you to notice now as x gets big, what's this going to do? That's going to go to 0, right? That's going to go to 0. And that's a constant, right? So we're not going to have a 0 in there. Okay. So now let's look at the limit as x goes to infinity of f of x. Okay, so as x is going to infinity, is it positive or negative? Positive. And the absolute value of a positive number is what? Just the number. So this is going to become the limit of the numerator, 10x cubed minus 3x squared plus 8. The absolute values, we can drop those out now because we know our absolute, it's a positive number. The absolute leaves it alone. We still have this square root 25 plus 1 over x squared plus 2 over x to the 6. All right. Now we'd like to get those reciprocal things involved again. So I really want to get rid of this x cubed. More importantly, I want to get rid of this x cubed. Because this x cubed is making this, what, get big. So I'm going to multiply by 1 over x cubed by 1 over x cubed. And what that's going to do is get rid of this x cubed here, and that's going to make this not go off to a big number. All right. Now remember, in the numerator, we have addition, so we have to what? Distribute. So we're going to get the limit as x goes to infinity of 10. When we distribute, I get what? Minus 3 over x. I get 8 over x cubed. Okay. And we had to distribute up there because it's what? Addition and subtraction. Down here, what's going on is this times this. That's multiplication. So we're allowed to what? Just this multiplication when you have the associative law. We pick two things and multiply them together. Well, I'm going to pick two things. I'm going to have you multiply them together. I want to multiply the x cubed times the 1 over x cubed, class. What is x cubed times 1 over x cubed? 1, right? They cancel out. So they cancel. That's the whole reason why I wanted those. And now I have square root of 25 plus 1 over x squared plus 2 over x to the 6. Okay. So now let's let x get big. As x gets big, what happens to 3 over x? That goes to what? 0. What happens to 8 over x cubed? That also goes to what? 0. What happens here? This goes to 0. This goes to 0. That reciprocal law that we studied last Wednesday was important. All right, in the numerator, what do we have left in the numerator? Just 10, right? What do we have left in the denominator? Square root of what? 25. Yep, and because these were 0, right? And that's what? 10 over 5. And what's 10 over 5? 2. So what is that saying? We have a horizontal asymptote y equals 2 as x goes to what? Infinity. Okay, and that's what? The right-hand behavior. Now we still need to what? Look at the left-hand behavior. All right. So now let's look at the limit as x goes to minus infinity of f of x. All right. Now we've done a lot of that algebra, so we don't need to reinvent fire twice in the same class. So we'll go ahead and put a few dots there and go ahead and make this the limit as x goes to minus infinity. And I want to get back to that step where I have the absolute value there. I have the absolute value of x cubed. I have the square root of 25 plus 1 over x squared plus 2 over x to the 6. Up here I have 10x cubed minus 3x squared plus 8. So I went back. It's all the same algebra. All right. So now x is negative. How do I take a negative number and make it positive? I change its sign. So this, when we take it, because we're going negative, that's going to become minus x cubed. So that's going to be minus x cubed, 25 plus 1 over x squared plus what? 2 over x to the 6. And we'll still do that same game again. 1 over x cubed, 1 over x cubed. But now what's going to happen, this is going to become the limit as x goes to minus infinity. This is going to be 10 minus 3 over x plus 8 over x cubed. In the denominator, this is now going to be minus 25 plus 1 over x squared plus 2 over x 6. The only thing that happened there was that negative infinity, what? Added a negative sign. This still goes to 0. This still goes to 0. This still goes to 0. This goes to 0. The numerator goes to 10. Where does the denominator go to? Minus 5, which would be what? Minus 2. So what do we have as well? We have a horizontal asymptote y equals negative 2 as x goes to negative infinity. So I can tell you a lot about this graph already. I can tell you it has a horizontal asymptote there and there. So as we're going out this way, I know it does something like that. And as we're going up this way, I know it does something like that. And give you a chance to get those written down. And then let's look at the graph of this real quick. And then we are out of time. And this concludes 2.5. All right, so oops, wrong keyboard. So let's look at this graph real quick. Oops, Alt, Tab, oops. Oh, there we go. Okay, Wrong mouse down. All right, so let me just go ahead and back this up. So we had 10x cubed. Oops. $10x cubed minus 3x squared plus 8. And then down in the denominator, what did we have? We had the square root. So to get to the square root, you can type SQRT. Oops, but it can't be cap locks. SQRT. And then it started parenthesis. And that, notice it brought a square root up. And what was it again? 25x to the 6th plus x to the 4th plus 2. And then let me go ahead and just turn those off. And oops, I didn't hit enter. You got to hit enter before you move around or you mess yourself up. My bad there. 10, but I made it a learning experience, so that wasn't totally lost. Minus 3x squared plus 8, tab down there, f of x equals 10x cubed minus 3x squared plus 8 down to the denominator, square root of 25x to the 6th plus x to the 4th plus 2, hit enter, and now, does it look like, oh, that's kind of an interesting graph. So calculus later, we'll learn how to find this point, we'll learn how to find where this is. Does it look like it's going to y equals -2 on the left and y equals +2 on the right? Now, I thought it was going to come from below. It looks like it's coming from above. And we'd have to do more exploration. All right, so we have the ability to do left and right hand behavior. We have the ability to look at polynomials, tell quickly. We also have the ability to look at rational functions and tell quickly. All right, and we are out of time. So thanks for coming today, and we'll see you tomorrow. And I'll get those quizzes graded tomorrow or today so we can get them back tomorrow. So I think everybody took them in this class.